All right. Hello, everyone. My name is SoaresSantos. I am a professor here at the University of Michigan, and my area of research is in cosmology, using large-scale sky surveys, such as the Dark Energy Survey, where that's the main collaboration that I am a member of. And today, I'm going to talk about the program of doing cosmology studies in the era of multi-messenger astronomy. And I will clarify what I mean specifically about multi-messenger observations here. I always like to start this type of talk by showing this image, which is one of the images that I am most proud of. What you're seeing here for the non-experts in the room is a pair of images taken 2 weeks apart with similar conditions. The instrument that was used to take these images is called the Dark Energy Camera, DECam for short. It's a 570 megapixel camera installed on a 4-meter telescope in Chile. That is the type of instrumentation that we use in the DES collaboration. And what you're seeing here, highlighted by the crosshairs, is the source corresponding to an event that we call GW170817. This is a gravitational wave emitting merger of 2 neutron stars that occurred on the 17th of August of 2017. You notice that in this field, our naming convention is very boring. It's just GW and the date when the event happened. So what you're seeing here is the electromagnetic, so the part of the electromagnetic emission corresponding to the aftermath of the merger. This is within the first 2 days of the merger. It's a combination composite of images that we took. And this bright spot here is the galaxy in which this merger happened. So you can imagine, you can see that the galaxy is big. It covers this entire area here. This here corresponds to the core brightest spot in the galaxy, in that galaxy. And the binary merger happened here somewhat at the periphery of the galaxy. And as you can see here on this other side, 2 weeks later, that bright spot is gone. So what this means is that, first, this explains what do I mean by multi-messenger astronomy. I mean that there is gravitational wave emission, which you're not seeing here, but was collected by the gravitational wave detectors, LIGO and Virgo. On the other side, there is electromagnetic emission. So the multi-messengers here are gravitons and photons. And in particular, my specialty is in collecting photons. So oftentimes what we do is what we call follow-up observations. So we get the trigger from the gravitational wave detectors and we point in that direction, trying to catch the short-lived transient source that corresponds to that event. Okay, so excellent. So why do we do this other than the fun thing about this, detecting and discovering something so beautiful and ephemeral in the sky? Why bother? Why going through all this pain to detect this tiny little dot in a sky of billions of objects? This is what I'm going to turn to next. So as I said, my motivation in the world of physics is to study cosmology. What does that mean? I want to understand the history and evolution of the universe as a whole. And in particular, I'm interested in making measurements of things like the rate of expansion of the universe, the change in this rate of expansion, if it's constant or if it's accelerating or decelerating. And with that, I want to infer what are the components of this universe and how they interplay and interact with each other. We know that we physicists, we have been extremely successful in understanding the fundamental pieces of nature and how they work, in terms of the fundamental particles and the fundamental interactions and etc. But we know that that corresponds to only approximately 5% of the total content of the universe today. So we still have a lot of unknowns ahead of us. So the study of cosmology is something that is vast and exciting. In particular, there is one parameter that I want to call your attention to in this slide. This parameter is H naught, the Hubble constant. It corresponds to the rate of expansion of the universe today. So if you think of, so if you look at the unit here, what this means is that if you think of a box in the universe that has a size of 1 megaparsec cube, we know that the side of this box is growing by approximately 70 kilometers per second. Okay, that's the rate of expansion of the universe today. It is a big achievement of our community, the fact that we can measure this number. And more than that, if you look at the size of the error bar, so each of these points here correspond to different measurement with a different observable and different team of physicists too. You will see that, I mean, the error bars here are a couple percent. So we know these numbers with a very good precision. Now, more interesting is if you ignore the details here in this plot and pay attention to this set of points here, these points in red correspond to measurements made using supernova observations. And I'm not going to the detail of how they do it, but they do these measurements very carefully using supernova. And here is a very precise measurement as well, using the maps of the cosmic microwave background. That means radiation from the early universe that is detected in the microwave wavelength by the Planck satellite in this case. Notice that this is very precise, it's 1% error bar, and it's discrepant. These results here disagree with these results significantly. This plot is a couple of years old, no more than a couple. This plot's from 2016, and if you look for a new version of this plot in the literature, you see that the error bars are getting smaller and the discrepancy is getting bigger, more and more significant. What does that mean? It means that we have a tension between these measurements, and as you can imagine, every time that something like that happens, when you have different experiments getting numbers that disagree with each other, there are at least two possibilities. One of them is that there are systematic uncertainties or something going wrong with either or both of the experiments. That is unlikely, but not impossible. On the other side, it is possible that the physics model that we're using to interpret these measurements is incomplete. And in particular, here, I like this version of this plot, although it's a little bit old, because the authors did me a favor here of putting these arrows up here. What these arrows means is if I make a change in certain parameters of the cosmological model by a certain amount, this is by how much the results from Planck would come into agreement with the results from supernova. The author of this paper is a supernova person, so of course the arrows go this way, but you understand the picture, right? That you would get better agreement if you change the physical model. And in particular, there are many parameters that you can tweak, but in particular, I will call your attention to these two parameters here. They correspond to the equation of state of dark energy. And the idea being that if you imagine that there is a fluid in the empty space between galaxies that is causing the expansion rate of the universe to increase, so causing the accelerated expansion of the universe, these two parameters are governing the microphysics of that fluid. And if we change this fluid, the most accepted model for it is the cosmological constant from Einstein. But if we change from cosmological constant to something else by say 10%, we would already create an agreement and so on. So it's really important for us, if we really want to get to the bottom of what is going on with this discrepancy here and try to understand what really is the rate of expansion of the universe, what is going on with the acceleration of the expansion of the universe, and what is the microphysics that is happening there, we need to get better measurements. We need to get better, not only more precise, smaller error bars, but we also need to get very accurate measurements so that we can disentangle this discrepancy and see if it is systematic uncertainty or if it is really a smoking gun of physics underlying the processes here. In order to do that, if you're a physicist facing this problem, you have a few options, right? If you're in the supernova camp, you may probably decide that you're going to make beautiful, more precise, get more supernovae, study them in more detail. Same thing if you're a CMB person. But if you're in neither camp, you may want to add a new measurement using a different observable, neither supernova nor CMB, that could arbitrate between between these two. Something that is independent, that is of high precision but independent. Okay, and what you see here is a number of measurements using different observables, but none of them is even close to the same level of precision here. Okay, but I claim that gravitational waves, the multi-messenger observations of which this here was an example, I claim that that is going to be a promising way to disentangle this. Okay. So before I dive into that, let me spend 1 minute introducing the Dark Energy Survey, which is this product I work on. As I said, it's we use DECam, a 570 megapixel camera with 3 square degree coverage in the sky. We use this camera to survey 5,000 square degrees. For non-astronomers in the room, this is about 1/8 of this, the entire sky. And we also observe supernova, and we do the gravitational wave follow-up observations, trying to combine multiple observables in order to make plots like that you've seen before. This is a version of a recent plot that we made. It's a recent result with other cosmological parameters, not H0. I won't have time to go into detail about this today. I can explain more if people want to ask during the discussion. So let's go dive into the gravitational wave side of things. How do gravitational waves help? There's a concept there that I need to introduce, that is standard sirens. The idea, which was first proposed 30 years ago, this paper is a good example of that. It is a very neat paper. Oftentimes, I think that undergraduates shy away from reading original papers and prefer to go into textbooks and so on. In this case, I really encourage people to go after this paper and read it. It's short, 3 pages, and very on point. The idea here is the following. In order to make measurements of the H0, we want to make a plot of distance versus redshift. And the distance part, the redshift part, is relatively easy. You make the spectrum and you identify the lines corresponding to the different elements and by how much they have shifted. Now, the distance part is the challenging one. And gravitational wave events can be used as standard sirens to get the distance, thanks to the fact that GR, general relativity, it provides a very clean way to measure the distance to a binary source. What happens there is that you can imagine that as a binary system goes closer and closer to collapse, the orbit decay of this system is happening because gravitational waves are being emitted, right? The system is losing energy in the form of gravitational waves. As the system gets closer and closer to the merger, the rate of change in frequency, dF dt, this shown here, depends on the combination of the masses. This is the sum, and this is the reduced mass of the system. Okay, it depends on a combination of masses with some powers here. Okay, now, as it turns out, the amplitude of the waves also depend on the combination of the masses, and it's the same combination with the opposite powers. So what does this mean? It means that if I have a detector and I catch these gravitational waves, I can measure the rate of change in frequency, dF dt, in my signal. And with that, I have the intrinsic amplitude of the waves. And then I can compare that intrinsic amplitude with the amplitude of the waves that are detected in my device. And the ratio of the two will give me the distance. So it's a very clean way of measuring distances for binary systems. And by clean, I mean you don't really have to take into account a lot of the astrophysics math that usually goes on in these systems, okay? So this is a motivation for us to try to seek these objects, because if you get the distance from the gravitational wave signal, and if you find the object in the sky, you can put this object in a distance versus redshift plot and measure H naught, okay? So here is a plot showing how hard it is to find these objects in the sky. In particular, I call your attention to this side here, where we show the area in the sky. Remember, our camera has a 3 square degree field of view. And here we are talking about tens of square degree field of view. And this x-axis shows the confidence level, meaning what is the probability that the source is inside that area. So to summarize here, you see that you have to cover approximately 60 square degrees to have 90% confidence that the source is in there. And the different 2015, 2016 correspond to different configurations of the gravitational wave detectors. We are way past 2016, we are in this regime here. So 60 square degrees for somebody who has a 3 square degree field of view camera is not too difficult. It's not easy either, but it's not too difficult, right? With 20 shots in different, like if you are going to make tilings of the sky, with 20 shots, you cover that area. So it is something that is that we can do. So in practice, how does this happen? In practice, as I said, we watch for triggers coming from the LIGO detectors. These are the gravitational wave detectors. When they catch, the gravitational wave signal, they will make a sky map saying, here's the region of the sky where we think the object came from. We take that sky map and we make our observing plan. We send to the mountaintop, where our colleagues will run this script and obtain images. We then process these images through a computing pipeline and produce a list of candidates, which are, little dots in the sky that could be the optical counterpart. And then from there, we will make a discovery of the counterpart. This is showing how long it takes for this blue part of the diagram to happen, the image processing itself. So let's show this in action with GW 170817. That's the great success we've had so far. As I said, the event happened on August 17, 2017 at a distance of 40 megaparsec. So 40 megaparsec is really very close in terms of cosmology, but it also meant it was easy to detect. We were not the only team that was working on this. Lots of people all over the world were interested and had signed up to do this work. So at the end, the papers that came out had literally 1,000+ authors, and our team was one of many, working on this. So in order to look for a counterpart, it helps to know what you're looking for, right? So let me overview in one slide what are the physical mechanisms that produce the electromagnetic counterpart of this event. The idea is the following. You're thinking of a binary neutron star system, so 2 neutron stars merging. What happens is that very close to the merger, the tidal forces are so extreme that not even the super hard neutron star material can withstand it. So what happens is that you have a disruption of the neutron star, and neutrons, as you know, when they are free, they are not stable, right? So what happens is that we have nuclear reactions that happen in chain, and those nuclear reactions produce elements all the way up in the periodic table to the lantanides. Many of those elements are also radioactive and will decay into more stable ones, and etc. It will be a mess. But in this process, the big important thing that will happen is that there will be a lot of heat being produced. Okay, so this heat is a source of thermal emission that is going to be detectable, or that's the thing that we are going to look for. In addition to that, these systems have very strong magnetic fields, and that causes some of the particles to be accelerated really, really fast, and that produces relativistic outflows that are not thermal, and they're beamed in a certain direction. These relativistic outflows for us are not so relevant because my camera is sensitive in these wavelengths, not these ones, right? Of course, but these are also present. Okay, so these are the two signatures that you can look for. Again, this is the one that matters for us today because that's the one that we can see with DECam. The physical parameters that govern how bright and the emission will be are the mass ejected. That's typically 1% of a solar mass. The remainder of the mass all collapses into a black hole at the end, right? So it's 1% of a solar mass approximately. The velocity of the ejecta, which is 10 to 30% of the speed of light. And another one, which I didn't put here in the slide, which is the opacity of the material, okay? So those are the relevant parameters. So GW 170817 was a multi-messenger event in the sense that the gravitational wave signal was detected. This is the frequency versus time plot. From this plot here, you can measure the DFBT that I mentioned earlier, okay? And 2 seconds after the merger is happening here, times t equals 0. 2 seconds after the merger, 2 gamma ray detectors were capable of capturing the result of this process here and detected the counterpart. If the story had ended here, GW 170817 would already be an event for the history books, okay? Of course, I would not be so happy because I don't work on gamma ray wavelengths. I work in optical wavelengths, but it would have been already spectacular. Now, there was more, right? The next thing that you do here is to try to find the source. I am particularly interested in finding the source so that I can get its redshift to make my cosmology measurement. So here it's showing the challenge of finding so this is the localization region in the sky, okay? This region here has, it was approximately 40 or so square degrees. So it's comparable to the number that I mentioned before, which was 60 square degrees, right? The other blue regions here are corresponding to the localization area from the gamma ray satellites. They are not very good at localizing their signal either. And here's a zoom in that region from a paper from one of the other many teams that were looking for the counterpart, the SWOPE team in particular. And what is interesting here is that these guys, they have a small telescope with a very narrow field of view. So instead of scanning the entire region, what they did was identify a list of galaxies that were in the region of interest. Those are the circles. And they pointed the telescope to each individual galaxy, or fields containing a couple of galaxies to try to find a counterpart. Okay, and this was the way they did it. We did it differently. We have like a cannon, right? I can see a large chunk of sky at once. So we covered the entire thing. And this is his picture I like a lot because it showed some members of our team who were in Chile taking the data and looking at the images. At the same time, some of us were at Fermilab here in Illinois, near Chicago. And there were people all over the place. Our team is very international, and everybody was looking into the images, trying to see it. And remember, I mentioned in the flow chart that the images were being processed, right, automatically. But at the same time, 40 megaparsec is so close that we knew that by eye, in the raw images, we would be able to identify it if it would be there. And in fact, one of our colleagues at Ohio University, he did identify the counterpart by eye in this image. And this was something that I have to say I had never, until that point, and never since, then experience such an excitement moment of discovery, you know, because we were really like, oh my God, this is it, we found it, right? And so what's the protocol when this happens? Here, if you don't know about this, the protocol is that we write a message to an alert system called the DECam system, and that report is what serves first to claim that you're the first one to see it, and also to spread out the word to the community so that other people can look there at that candidate. At this point, it's just a candidate, right? Look at the candidate and confirm it or not, and so on, right? So I am there literally typing as fast as I can. When I look to my email, there is a message coming up from, guess who? The SWOP team, the guys with the tiny telescope with a narrow field of view. They saw it too, and they beat us by exactly 9 minutes in reporting in the system. We also sent our report, and at the end, our teams were acknowledged as independently discovering the system. This is their image for completeness. I like to show. It's a little bit blurrier than ours, I have to say, but there it is. Here's the source. And I think it was a humbling and interesting experience to see the success of so many teams. And in fact, there were 6 teams that independently from each other discovered this counterpart and reported it, and this is their list for completeness. So now what happens at this point? I hope you are all first excited to see this beautiful result. As you know, GW170817 was considered the result of the year by the Science magazine in that year, 2017, and it appeared in the New York Times front page and etc. It was a big, if you're in the world of physics, paying attention to what's going on in physics, you probably remember seeing a lot of talks about the discovery and about everything, right? So what I'm saying, a lot of what I'm saying here is not really new. It's just telling the story from the perspective of our team. So at this point, then you should think, okay, 2017 was far in the past. What has happened since then, right? And we started thinking about that right away. And the first thing that we knew is that 40 megaparsec was exceptional. Then most of the events would happen at 100 megaparsec plus, okay? And so one of the big questions is, could you see this source if it would be further away? Should we improve our search strategy to be able to see this further out? There are other relevant questions as well. For example, it looks like this is the counterpart, but convince me that this is really the counterpart and not just some blip in the sky that is masquerading as the source. So we answered these questions and more in the paper that we published in 2017. I'm not going to have time to go into detail, but what we did basically was introduce simulated events in the images and process them and use our automated pipeline to say, let's forget that we know where the counterpart is. Let's use the algorithm and see if the algorithm finds the same source as we found by eye. And the answer is yes, everything looks consistent and looks great. Okay. Now, what about cosmology? We said that our motivation to do all of this stuff was to finally use this event for cosmology. So remember that the exercise is to make a plot of distance versus redshift and fit a straight line to it. That's the H0 measurement, okay? It's a little bit hard to do that with only one event, right? So to fit the line through one event, but we did this. And this is the result. This is a posterior distribution. This is H0 again. The vertical lines represent the measurements from supernova and CMB. It's another representation of the 2 most extreme lines from the plot I showed earlier. And this is the measurement. As you can see, the uncertainty is huge. That's what you expect with only one dot in the plot, right? But it's consistent with both, right? And this is from only one event. So I'll skip this and say in the interest of time, I think I will have to skip a few things. But let me say that this is for one event. So you may ask the question, okay, how long should we wait until we get to the point of actually, making measurements that are this narrow, I want this distribution here to be so narrow that I can distinguish between orange and green here, right? And this is one of the questions I'm going to answer towards the end of this talk. So if you pay attention to what's going on in this field, you will see that we have not had another event like GW170817 yet. That was the one and only event that has an identified optical counterpart today. Even though LIGO has detected dozens of other gravitational wave events, that's the only one that has a counterpart. Why? Part of the reason for that is the fact that most of the events that LIGO has seen are binary black hole mergers and not binary neutron star mergers. And so in that scenario, the physical mechanism that I described of the neutron star disruption, etc., well, there's no neutron star, so that mechanism doesn't apply. So what we did in our team was we said, like, look, maybe there is some other mechanism that we don't know of that produces it as a magnetic counterpart. Let's look. We looked. These are two examples of events that we mapped out looking for the counterparts. And we found nothing. If we had found something, I would be telling you, but we didn't, okay? What we did instead was to say, okay, maybe we can salvage this. Maybe we can use the gravitational wave events that don't have a counterpart as probes for H0 anyway. How so? The idea would be that instead of associating one galaxy redshift with one distance, one-to-one association, we would now associate one gravitational wave event with a distance with a distribution of galaxies. And here's an example. This is an event, binary black hole merger event, that also happened in 2017. This is the 90% localization in the sky, and the colorful map shows the distribution of galaxies. You can see that there's a clump of galaxies here, more or less aligned with the high probability region. So the idea here is that because the galaxies are clumped in the sky, you could say that there is an overall probability, right, that clump, that the one galaxy in that clump is the counterpart. So as you can expect, the measurement here will be worse on an event-by-event basis. It will be worse than what you would get with a one-to-one association. But because these events, they outnumber the binary neutron star ones more than 50 to 1, maybe, only maybe, we would be able to win by combining enough events. And this plot here, which I'm not going to describe in detail, it is made with simulations. And you can see that after 100 events, you can converge to the right value, the simulated value here of 70 of H0, okay? So we decided to apply this method to this one binary black hole merger. And this is the result that we got. So this curve here, so again, the vertical lines are supernova and CMB. And the gray contour here is the result that we obtained with GW170817. And the red, which is much broader, is the distribution that we obtained with this black hole merger. As expected, it is worse, meaning the posterior is much broader, but it is still consistent with the overall picture. The peak is more or less the right place. And more than that, it is something where perhaps combining many of these events would shrink this into a result. So all of this, as if you notice, we are talking about data from 2017. As you probably know, the LIGO detectors have produced more events since then. There were in total so far, there were 3 observing campaigns of the advanced LIGO and Virgo detectors. The results we are showing here was the observing campaign number 2, O2 for short. Then there was a pause of about a year, and then we had the 3rd observing campaign that was from April 2019 to about March 2020. And during this 2nd campaign, there were many more events, but our team in particular we focus on 3 of them. These are listed here. These 3 events, they were special. Each of them was special in a different way. 2 of them were events that had at least 1 neutron star in place. So that's good, because then the mechanism of disruption of the neutron star, etc., applies. This other one was a black hole merger, like many others out there, but this was special because it was very well localized. The area in the sky was very small compared to other black hole mergers out there. Okay, okay, let's try to summarize the results. What I'm going to do is the following. I'm not going to go over, we're still analyzing this data, but I'm going to go over the results for these 2 events here that possibly contain a neutron star. This one, I should say, that is an event. What do I mean by NSBH? I mean that one component is a neutron star, the other one is a black hole. We think that that is the case based on their masses. But it could be that it could be a very asymmetric black hole merger as well. But under the hypothesis that it is a mixed NSBH event, we try to do a search, and we are going to interpret the results here. So this is what these 2 events look in the sky. These are 90% and 50% localization regions, and the hexagon shapes here are the footprint of our camera on the sky. Okay. And this is the same for the other event. These 2 papers describe in detail our search strategy and the results, etc. I recommend that you have a look at them if you want to know more. As I had mentioned earlier, the 3 physical parameters that matter to how bright or how faint the events are ejected mass as a small fraction percent or so of a solar mass, velocity of the ejected material, also up to about 30% of a solar mass, and opacity, which we parameterize by lanthanide fraction. So basically, if the reactions go too deep into the lanthanides in the periodic tables, those materials are very opaque, and that means that very few photons will be able to escape that hot mass of material. And that means that the object will appear fainter to us. And it will also appear redder, by the way. But for the purpose here, let's concentrate only on the total luminosity. So what you're seeing here in these heat maps, yellow means high probability that if the object was in that patch of sky, we would have seen it. Blue means low probability, because the object would be too faint, okay? And it makes sense. You can imagine that higher opacity means more difficult to detect. Lower mass ejected also means more difficult to detect. And a higher velocity also means, it can mean more difficult to detect, okay? So these parameters, they are correlated, and then sometimes it's complicated, but that's the overall trend. This spot here corresponds to what GW170817 looked like. As you can see, it was in the sweet spot here in terms of not too opaque, not too fast, enough mass, 2.5% of solar mass, etc. So if this event here would have been GW170817, we would have seen it. We did not see anything there. So it is possible that if really this event was a binary neutron star merger, as we think it was, it is possible that it was more opaque and so on. So we don't know, because with only one event, we don't have a population of these events to know if GW170817 was a typical event or not. But we didn't detect anything. So all we can say is that it wasn't there. Same thing for the mixed neutron star black hole merger. This one, as you can see, the map looks a lot worse. It's a lot more blue than yellow. Ideally, you want everything to be yellow, right? And the reason for that is that this event was much, much further away than the previous one. Okay. And so what about cosmology? I try to go back to my physics motivation every time. So here what we did was, okay, let's use the events from 2017 plus the best events from 2019 and combine them together. As I said before, the power of these so-called dark sirens, the dark one here means that the ones that you did not identify the bright component. The power comes from combining them together because each individually is not very powerful, right? And so we did that, and the red curve here now is a combination of these events. And you compare with GW17 or 817 alone, you can see that there is some improvement. The distribution looks a little bit narrower. It's not something to write home about, although we wrote in a paper. But it is a good sign. It's a sign that we are progressing towards, converging into a precision cosmology measurement. This gravitational wave business is still in its infancy, which I think it's good news if you're a student in the field right now, because it means there is a lot for you to do as it evolves. And to give a sense of how powerful this might be, I would like to finish by showing this plot here. So this plot is a projection that I made back in 2018. We had just finished the 2017 papers, and we were in the gap between 02 and 03 observing campaign. So I did a projection based on the expectation of improved sensitivity of the gravitational wave detectors, saying what is the expected number of events as a function of time for binary neutron star events in particular. And this is what this yellow curve is showing. The band here shows uncertainties on the rates. We don't know what is the intrinsic rate in the sky of these objects, of these mergers. And some periods of flatness like this means periods of time that the gravitational wave detectors are expected to be in shutdown for upgrades, okay? So as you can see, this is the log scale. So we are talking about a time frame, in a time frame of less than a decade, actually, like 5 years, right? Which is, I would say, very reasonable time scale if you're a graduate student or something. We are talking about growing by 2 orders of magnitude in the number of detections, okay? And this is absolutely spectacular. There are very few fields where you start, with a new type of technology, a new way of observing the universe, and then suddenly you grow by 2 orders of magnitude in data. And this is happening here. And so in the bottom part of this plot, what I did was to scale just the H0 measurement we did with GW17 or 817, the uncertainties here. And I just say, if I collect these many events and I just use statistical scaling, meaning the uncertainty scale with square root of n, this is how quickly we would evolve. This is assuming that all of the gravitational wave events have optical counterparts. If we don't, then you evolve a little bit slower. But you can see that 2% is the current uncertainties on the measurements done with supernova. We would surpass, or we would match, so to say, that level of uncertainty in a time scale of about 5 to 6 years. This is something that is, to me, I mean, I say that I should print this plot and put it in my wall, because on the days of doom and gloom, when I'm finding it hard to keep motivation, I look at this plot and remember this and say, like, no, let's pursue this because it's worthwhile. We are going to have a wealth of data, and being prepared to find the counterparts is important, because that's the best way for us to extract that information. Here on the side is a timetable showing, as I said, I'm a member of BES, which is the experiment that is the system that is in place right now, and did these observations that I'm showing here today. But more than that, we are constructing LSST, so the Vera Rubin Observatory, which is bigger, better, faster than the DECam. And by the time we are here, LSST will be operating, and we'll be able to have more efficiency in the searches for counterparts. Meanwhile, there will be also DESI, which is already on Sky today, and it's a a spectroscopic instrument that is helpful to confirm and do other observations too. So it will be an exciting field in many fronts. So in summary, I want to make sure that we leave time for questions. In summary, the so-called DESGW program, the program of doing cosmology with gravitational waves in DES, is leading, the charge of search and discovery of electromagnetic counterparts and doing cosmology measurements. It's been super exciting and fun so far. The third observing campaign ended in early in March 2020, and several papers already came out, more are coming, and I'll be happy to take questions. Thank you.
Thank you so much. It's amazing to just follow your story of your research, because as students, we're always given like the finished result or the finished theory or like the headlines, but just to see how it's progressed and like each stage as you've gone along is fascinating. I'm sure, well, hopefully people will have questions. I know I've got some. So do either turn your mics on and your cameras if you want to, or type your questions into the chat. I'll just start. When you say there are so many teams trying to spot this, are you in competition? Are you working together? How much of it is, oh, I want to be the first one, or how much of it is a collaboration?
Oh, everybody wants to be the first one to see it, right? But on the other hand, there is something very positive about making, it's a huge claim to say, here is the optical counterpart of this event, right? Especially in the early days for the very first one. So it is really good to have other teams saying, oh, we see it too. It helps to build confidence that it was just not a fluke or something, weird going on. But of course, everybody wants to be the first. Everybody wants to be, the first one to see it. But I think that we found in this scenario here, in this case here, we found a good balance between that sense of, competition and the sense of community, of being collectively going after something that we all want to pursue together. Another thing that's important also to mention is that different teams have access to different instruments, and so they complement each other in some ways. So for example, our camera is in Chile. So imagine if GW170817 would have been further north in the sky, we wouldn't be able to even try to look for it, because just you would be unlucky to be in a, say, wrong part of the sky, right? Or if it would have been much further south than it was, many of the instruments that were in the northern hemisphere would not have been able to see it. Another possibility would be, for example, sometimes there are clouds in the sky. And of course, we choose astronomical sites where the fraction of nights that you lose to clouds is small, but it could be unlucky. And then imagine, right? If you are the only team responsible for doing those observations, that would be very unfortunate if it happens, right? So there's some competition, but there's also a lot of complementarity. And so the community of people that are involved, I think they are very aware of both things.
And I was just wondering, with regards to that sort of equipment that you were outlining, some have sort of different cameras in different places. Is what's stopping us seeing these events purely sort of technical? And if so, sort of what developments do we need in order to get that sort of that progression that you outlined?
Okay, I think your question is, why haven't we been able to see more of those yet?
And how will we?
Mm-hmm. Yes, so I think that this type of plot here illustrates, and also a combination of this type and this type of plot illustrates the reason. So the regions in the sky are large enough. So the dots here are the individual candidates that we found. So the regions in the sky are large enough that it is not sufficient to, okay, so it's a combination of the size of the region and how far the object is. So as you know, the flux will go down with the distance squared. So, you know, these objects here, the distance, which I put on the slides, are, you know, you're talking about 200 megaparsec distances. Compare that with 40 megaparsec, and you see how much fainter in flux we are getting here, even assuming that the emission was exactly as bright as GW 170817, just because of the distance, you get a huge hit in brightness. So this means that, for example, if you have a small telescope with you know, a narrow field of view camera, you would have to be very lucky that it happened in one of the galaxies you're looking, and you would have trouble even then, because you have to invest a huge amount of telescope time to reach the depth that you need. So ideally, if you were to say, I want an instrument that's optimized for this science, ideally, you would have something that I keep calling like an ecosystem, where you would have something like DECam, wide field of view, and being able to scan large area going deep. And LSST camera will be something like that as well, right? And at the same time, you would have narrow field of view, also on a large telescope, to be able to go after individual galaxies that have promising candidates, and try to narrow it down so that you can optimize the search in both depth and area. In addition to that, there is something that you notice here, that we covered only about 70% probability. We didn't really cover the entire 90%. And part of that is that it's really a large area, you know, and we had to optimize and save on the telescope time and so on. So what it will happen on the gravitational wave side of things is that the experiments will become better at localizing. So we need more events like this that are well localized so that we can cover it with great depth, you know, and there are not many of those yet. And the reason for this is that the triangulation scheme works better when you have the 3 detectors capturing the signal. And because Virgo has lower sensitivity, oftentimes for these distant events, the contribution of Virgo is small. So what I expect to happen in 04, the 4th observing campaign, which we should start in about a year from now, is that the gravitational wave detectors all will get better, which means that for events that are similar to the ones we've seen so far, the areas will be smaller. And in addition, we are going to have more resources that we can put in combination, a coordinated effort, so that we can go deeper in the right places in the sky, and then try to make a discovery. But it could be also, that's the other thing that I should say, if we are unlucky and GW 170817 was atypical, if most events are here with high opacity and very low mass ejected, then it could be that the fraction, the subset of the events for which there are counterparts detectable at all is very small. It could be, we don't know yet, right? And if that is the case, then the dark sirens program, the one where you forget about the counterparts and focus on that statistical method using the galaxy distribution, that method will become more and more important. So we don't know yet. We're going to discover, you know, to figure it out in the next few years.
So yeah, more telescopes, sort of more specifically designed telescopes, and just better methods and things.
Mm-hmm.
Wonderful, very cool. Any other questions?
I was just going to ask, so you're trying to measure H0, but how is that going to explain discrepancy between the supernova and the CM?
Oh, yeah. So the idea should be, imagine a version of this plot where we would have our own data point with error bar. We want the error bar to be small, like this size or smaller even. And the question is this point going to be more aligned with the CMB measurement or more aligned with the supernova measurement, or in between, right? So if that new measurement is more aligned with the CMB here, What does that mean? It means that it is likely that our systematic uncertainties not accounted for in the supernova analysis. And it would mean that something like the cosmological constant is actually a good description, because this plot here is made assuming that dark energy is exactly the cosmological constant. It would mean that the cosmological constant is good description for dark energy, and it would mean that there is some systematic uncertainty not accounted for. It would mean also that it's like a conspiracy of systematic uncertainties, because these other measurements, although they are with larger error bars, they all tend to align with this side than this side. Some people call this tension the tension about early time and late time in the universe, because this is 300,000 years after the Big Bang, and these structures here form more recently, right? These observables. So it would be interesting to see if this measurement is on this side or this side. If the measurement is on this side, then it reinforces the idea that we are dealing with something that is physics that is different. And then what we want to do is to repeat the analysis, varying these parameters, and seeing which combination it better reflects the data. And this is good because then oftentimes what you want to do is to combine the multiple observables, and in this way, if the observables are independent, it is better, statistically speaking, it's better to combine them. So this would be a program I'm imagining in a decade from now. That is pretty much where we are going to be. The supernova teams, they are improving their measurements too. Their error bars are getting smaller and smaller. CMB measurements are also new measurements are coming and being planned. So in all areas of this field, we are making progress. It's a multi-pronged effort, right? And we're trying to make sense of all these measurements.
Oh, thank you. I know you need to rush off. Did you have time for one more question? Because I think Poppy has a question.
Sure.
Yeah, it's only a quick one. It was just, I know there's lots of other interferometers being built around the world. So I just wondered, how important is it to build new ones, essentially?
Fantastic question. I am really looking forward to Kagra, which is a detector being built in Japan, and LIGO India, which is being planned for India. The more detectors in the network, the better, because the localization areas will become smaller and smaller. And that means that our job of finding the counterparts gets easier and easier. So I'm all for it, and I can't wait until the network becomes bigger.
Okay, thank you so much. It's been fabulous.
Thank you. I really had fun. I have to rush now, but thank you so much.
No, thank you.
Bye-bye.
Bye. And thank you, before everyone else rushes off, thank you guys for coming. And if you do still have time, we've got 2 more talks left today, on Oppenheimer and then on aliens later. So please turn up for those. But thank you. Continue to have a lovely day.
Cool. See you later.
Yeah. Thank you.
Go and get